course. Check if the mic works fine. Yes. So basically, Laplace transform is a generalization for the Fourier transform. The Fourier transform integration from negative infinity to infinity, h of t is equal to negative j omega t dot dt. So this is what we call h of j omega, or h of omega for short. Now in Laplace, we will have a similar expression, h of s, and you notice s here is replacing j omega. So it's going to be exactly the same integration from negative infinity to infinity, h of t. Now instead of j omega, I'm going to replace it negative st dot dt. So if you compute this one, if you manage to understand how the Fourier transform mathematics work, then the Laplace transform should be no difference. However, to make it as generalization, S is typically sigma plus j omega. So if you consider sigma equals to 0, the Laplace transform will be the same exactly as the Laplace transform will be exactly the same as Fourier transform. So this is the arithmetic expression for the Laplace transform. We will add several, let's say, terminology related to the Laplace transform, concept called region of convergence. We'll also talk about stability, causality, and so on. So like from the Laplace transform, you can determine whether the function or the transfer function is stable or not, whether the transfer function is causal or not, and so on, or the impulse response. The new topic here, the region of convergence, basically, we will notice that like a function, for example, f of t, and another function, h of t, may lead to the same transformation. So Laplace transform, something like this. However, they are different. They have the same transform, but we will see that they have different region of convergence. We'll solve some examples on the topic to make things clear. So here is the objective of this lecture, something we already know from the Fourier transform. Assume you have a system h of t, and you have the input x of t and output y of t. The relationship between all these variables, that y of t equals x of t convolved with h of t. That is in time domain, we have convolution. In the Laplace domain, y of s equals x of s times h of s. So pretty much like what we did in the Fourier transform, y of j omega equal x of j omega times h of j omega. So here we can say h of s equals y of s over x of s. All right. So this is how we did the Fourier transform. We have the standard forward Fourier transform. We have the inverse, and we made a comment that doing the inverse is not an easy job. We use the tables to do that. And in many cases, we end up with like a coefficient a plus j omega. And the inverse for that one, Fourier inverse, is e to the power minus at, I believe. At u of t. And the unit step function u of t equal 1 over j omega, and so on and so on. All right, so this is just a quick recap about the Fourier transform. I just covered that in the first slide. Just put s instead of j omega. So that will be your Laplace coefficient. So the motivation behind the Laplace transform is just a generalization where s equals sigma plus j omega. So it is a generalization. It has several advantages over the Fourier transform. It can cover larger scope of signals or larger class of signals, and it provides additional insights. All right, so mathematically, this is how we represent the Laplace transform. So if you are given a function and you were asked to find the Laplace transform, just apply the integration and you will get the results. So as I mentioned here, that's the convolution part, and this is in time domain, and this one, the frequency domain, is just a multiplication. Okay, so the Laplace transform, the bilateral, because it covers both points in time from negative infinity to infinity. is given by this expression. Here is the inverse. As we mentioned, inverse is not that straightforward. It requires a lot of math, probably numerical analysis, not standard integration. So we use the pairs. All right, so a quick example here. X of t equals e to the power minus at u of t. So we'll open the whiteboard and do the integration from scratch. All right, so we have x of t equals e to the power minus at u of t. And we know the unit step function, that's the 0, and it has value 1 and 0 elsewhere. So that's the unit step function. And the exponential, e to the power minus at, so let's assume this is the 0. It's something like this. It keeps decaying until it reaches 0 at some point. So e to the power minus at, and this is u of t. So the result of multiplication of these two functions, I will get something like this. Notice the negative part is gone because of the unit step function. Now let's apply this to the integration. X of s equals integration from negative infinity to infinity e to the power minus at u of t dot e to the power minus st dot dt. So that's a multiplication operation. Now the unit step function, we've seen it like at the negative points in time, the values are 0. So here my integration will become from 0 to infinity because of the unit step function. It will do the effect on the negative points in time. E to the power minus at times e to the power minus st dot dt. So here if we are taking negative t as a common factor, so we have the integration 0 to infinity e to the power a plus s and the negative sign here dot dt. You can confirm, so e to the power minus at, so that's the first term, and I have e to the power minus st, that's the other term. Is it clear so far? All right, so here simply the result of the integration is going to be 1 over negative a plus s e to the power minus a plus s t, and the limits will be from 0 to infinity. And just to recall, the integration of a to the power alpha t dot dt equals 1 over alpha a to the power alpha t. So that's something we have done in calculus. All right, so to find the limits of this integration, or the result of this integration, so we can simply put the negative sign on top. So I will have negative 1 over a plus s times e to the power minus a plus s times infinity minus negative 1 over a plus s times e to the power minus a plus s times 0. Right? Okay. So what will be the values that we are getting here? So this one simply, that's going to be 1. And I have a negative and negative, so I'm going to get plus 1 here. Now, what about this one? So simply you can say, okay, a plus s times negative infinity. And you can say that's going to be like equal e to the negative infinity, right? So what will be the value here? 0. So in this case, the answer will be, negative and negative, a plus s. Negative and negative will cancel each out. So this is 1. I'm going to be getting 1 over s, and this is 0. So the answer here will be 1 over a plus s. However, we have to consider one thing. Now we assume that the value of a plus s is what? Positive. Why did you assume it's positive? So we have a positive number times negative times infinity, so that's negative infinity. However, if a plus s was less than 0, let's make that assumption. Will I get a value there? So if it was less than 0, so this is a negative number. By negative, so that's positive. So it's going to be e to the power infinity. So in this case, the integration does not exist. You see this point here? So to ensure this function gets value, a plus s should be positive. So in this case, s should be larger than negative a. And this is what we call the region of convergence. Region of convergence means that it is the values of s that makes the function exist. That like it will converge to, it will get to a decent value. Otherwise, the function will burst, like it will go to infinity. So basically, to find the region of convergence, you look at the exponent and you find the expression that will make this integration goes to 0. So in this case, if I want this code and the integration or this, sorry, exponential go to 0, a plus s should be positive. Because in this case, if it's positive times negative, that's going to be negative times infinity, negative infinity. However, if a plus s was negative times negative, that's going to be positive. Positive infinity, in this case, I will get infinity here. So in this case, my integration does not exist. So the region of convergence, just find that range of s. Now, in another example, now we will see we are going to get a different function and it will have the same exact Laplace transform, but the region of convergence will be different. All right, so I believe that's the solution. So here the result is 1 over a plus s. And this condition, a plus s is larger than 0 to ensure this integration will go to negative infinity, to go to 0. So this is the region of convergence. And if you want to draw it on the S-plane, so there's something also called the S-plane. S-plane basically, this is the S, and you have the 0, the center, so negative a is somewhere here. So in this case, so this is negative a, this is my region of convergence, ROC. If like for some reason you were required to plot the region of convergence. And also a is assumed to be positive integer. Like a should be larger than 0. Otherwise, if a is negative, then you will have negative by negative, that's going to be positive. So the function will be something like this if a was negative number. All right, now let's see this other example. X of t equal negative e to the power negative at times u of minus t. So let's take it here. Another function, x of t equal negative e to the power minus at u of negative t. Let's confirm it's exactly the same. Negative, yes. All right. Now, u of negative t, so what transformation we're applying here to the step function is time reversible. So it is something like this. So this is u of negative t. Okay. So let's apply the expression and this exponent e to the power negative at, something like this. By multiplying by the negative sign, so it will be flipped like. That's the amplitude transformation. I'm doing an image over the x-axis. All right, so let's do the math. X of s equal integration from negative infinity to infinity, negative e to the power minus at, u of negative t, e to the power minus st dot dt. So the unit step function here will do effect on this or on this, on the upper one, because now my limit after 0, there is no values there. So in this case, my integration will become integration from negative infinity to 0, negative e to the power minus at, e to the power minus st dot dt. So let's take previously, like in the previous example, to 0, have negative a. So negative a plus s t dot dt. So is it clear up to now? All right. So what will be the integration in this case? So let's keep the negative sign here. I'm gonna get negative 1 over negative a plus s. I'm doing negative without this negative because I already put it here. E to the power minus a plus s t. And the limits from negative infinity to 0. All right, so let's assume I have it here, assuming I took the negative sign outside. So the integration will be negative 1 over a plus s, and I'm going to get the same exponent. Clearly, I can remove the negative signs here. Now let's apply the limits of the integration. So initial substitute 0, 1 over a plus s, e to the power minus a plus s times 0 minus Now let's apply the infinity part. 1 over a plus s e to the power minus a plus s times negative infinity. All right, so this one clearly is going to be 1 over a plus s minus, all right, so let's see this expression. So I have a negative sign here, and I have a negative sign here. They will cancel each out. So I have e to the power a plus s times infinity. So at, like, say, initial guess, someone might think, okay, so this one is going to be infinity, right? Because it's e to the power infinity. However, if a plus s is less than 0, what will be the result for this? 0. So it's going to be minus 0. However, what is the region of convergence? A plus s is less than 0. So s less than negative a. Clear, Zena? Okay, so I'm having e to the power a plus s times infinity, right? So initially someone might think, oh, so it's e to the power infinity, that's going to be infinity, right? So that's where the function, what they call diverge, it will not converge. How to ensure this function will converge? By converging, like, it will go to 0 if this expression a plus s equals to a negative value. Because if I have it as a negative value, then I will have e to the power negative infinity. So in this case, it will become 0. So how to make this one a negative value? So a plus s is less than 0. So the condition for s is to be less than negative a. So in this case, this will go to 0 if s is less than negative a. Otherwise, it will go to infinity. All right, so in this case, if s is less than negative a, then this exponent will become a negative exponent, e to the power negative infinity, it will become 0. So this expression will be gone. So in this case, I have 1 over a plus s minus 0. So it is 1 over a plus s. However, my region of convergence equals to what? S less than negative a. So if you look at this expression, it's the same exact Laplace transform of the previous one. However, the region of convergence is what? If I'm looking, this is the 0, this is the S-plane, so this is negative a, that's the region of convergence. In the previous example, the region of convergence were the other side, the one larger than negative a. So here in the slides, kind of summarize it. So in this case, okay, where's the marker? All right. So yeah, that's the region of convergence when a plus s is less than 0. So s is less than negative a. And it is the same exact Laplace transform than the previous one. So here, and when you do the Laplace transform, you also have to provide the region of convergence. As we notice here, two different functions in time domain led to the same exact Laplace transform in the Laplace domain or frequency domain. Is it clear for now? All right, so that's the region of convergence. So that's for the previous one when we have e to the power negative at u of t. And this one is for the other function, negative at u of negative t. Both of them led to 1 over s plus a, or a plus s. So notice in both examples before, Laplace transforms look the same. The integrals got different values for the real part of s. So when taking the Laplace transform, you must take into account the region of convergence, which is the range of values of s, which the expression is valid. So this is the representation of the region of convergence. That's for the first one, and that's for the other function. Okay, similarly to the Fourier transform, so we have some properties. Basic property here is the linearity. You have x1 of t, and you have x2 of t, and they are weighted and added. Weighted multiplied by a1 and a2, and then they are added. Their Laplace transform is basically a1 x1 of s plus a2 plus x of s. Now, what will be the region of convergence in here? It will be the intersection for the region of convergence of this one and the intersection of the region of convergence of the other one here. Means that, assume that I have x1 of t, the region of convergence is s larger than negative 2. And x2 of t, the region of convergence is s less than 3. So what will be the region of convergence of x1 of t plus x2 of t? Is basically the intersection between those. So the previous one, I have at negative 2, so it is this region, s larger than negative 2. For the other function, 3, it is this region. So what is the intersection? Is this one. So the region of convergence for their addition is s larger than negative 2, less than 3. Got it? So that's the first property, and that's the one that will be, let's say, considered. Time domain shifting, pretty much like in the Fourier domain. When we do shift in time domain, we scale by an exponent. So here we have e to the power minus st naught x of s, and the region of convergence is all real numbers. The Laplace domain shifting here is the opposite. Okay, mainly will be, let's say, dealing with those two actually. The conjugation, convolution becomes multiplication. Another important thing here, we'll use it also to solve differential equations. A derivative will lead to multiplication by s. So d over dt of x of t will lead to s x of s. Now d2 over dt square of x of t, that's the second derivative. What will be the Laplace in this case? S square. So dn over dt n of x of t, so that the nth derivative will lead to s to the power n x of s. I went away to other slide. Clear? So in there it was j omega. Here is just s. And you notice also it's simpler than the one with the Fourier, because in the Fourier we have j omega. So when you have j omega squared, it becomes negative omega squared. You have j omega cubed, it becomes negative j omega cubed, and so on. There will be a sign changing in the Fourier, but here it's just s in Laplace, so it is easier. When you multiply by t in the time domain, you differentiate in the Laplace domain. We don't usually use it. We use this one mainly to solve differential equations. Integration is going to be the opposite. If you differentiate, you will get multiplication by s. When you integrate, you divide over s. Something you will do, inshallah, in the control systems class when we analyze electric circuits with Laplace domain. You notice that for a capacitor, like the voltage will be negative infinity to t, I of t dot dt 1 over c. So that's the voltage of capacitor, for example. It will become 1 over s c I of s. That's the VC of S. More details about it in the future, inshallah. All right, so here are some pairs. Delta function will lead to 1. The unit step function, we have to memorize it, or you will be provided with the tables, but rather than just looking at the tables, just u of t by default is 1 over s. Negative u of negative t, it led to the same exact Laplace transformation, but the difference will be in what? The region of convergence. So in this one here, the region of convergence is s larger than 0. Here, the s less than 0. So the difference is in the region of convergence. All right, so another expression here, there. So notice also they are similar in terms of Laplace, but the region of convergence is a bit different. One common one we'll be dealing with is this one. It will be beneficial for us because when we apply the inverse Laplace transform, usually when we do partial fraction expansion and getting, let's say, a over s plus alpha plus b over s plus beta, and you have by partial fraction expansion, you have to find the values of uppercase a and b. So in this one will be a to the power negative alpha t plus b e to the power minus beta t. And you always assume you multiply by the unit step function to ensure the system is causal. All right, so that's something like this that we'll be dealing with a lot in the class. Similarly, like most of the transformations are in pairs, just to show you that the region of convergence is different for both, let's say, equivalent Laplace transforms. All right, so those are the common ones, actually. We'll be dealing a lot with this and this. Okay, here's an example. Find the Laplace transform of x of t equals 1. So you just apply the integration. I'm not gonna put some time into this. So here, negative infinity to infinity, 1 e to the power minus st. In the slides, they did it in a, let's say, weird way, let's say. So they separate the integration. You know, the integration from a to b equals integration from a to c plus integration from c to b. That's something you have done in calculus. So they separated the integration and find the transformation for each one of them with the region of convergence, and they realize that there is no intersection of the region of convergence, so in this case it does not exist. Because the first one, the region of convergence is less than 0. The second one, region of convergence is larger than 0. And since you have addition of these two functions, then it should be the intersection. There is no intersection. Or you can simply do it like this without doing this separation. So I will have here in this case negative 1 over s e to the power minus st, and my limits from negative infinity to infinity. So the first one will be so I'll put the negative 1 over s on the side. So I have e to the power minus s infinity minus e to the power s infinity. Because I have negative infinity by negative s, will become s. All right. So here, what is the region of convergence of this one? S should be larger than 0. And in this case, S should be less than 0. Do the intersection, there is no intersection. So there is, like, this transformation does not exist because there is no region of convergence. You cannot have a Laplace transform without a region of convergence. Okay, so here in this case, Laplace does not exist. You get the idea here? So there is no need to separate the integration and consider them two functions. You can take for both, and you notice for this one, the region of convergence, S should be larger than 0. In this case, it's the opposite. S should be less than 0. Another example here, e to the power minus t u of t plus e to the power 2t u of minus t. I think we've done something similar for this. You can also rely on the tables. And yeah, the first one, e to the power minus t u of t, it is 1 over s plus 1 from the table. And in this case, the region of convergence s should be larger than -1. You refer to that one here. So I have the first one. So s larger than -1 because it will minus 80. Then the other one here, e to the power 2t u of -t. And you have it here. So a is -2 in this case. And you will get -1 over s plus a, which is 2 in this case, -2. And that's the transformation. I have a negative sign. The region of convergence is less than 2. So the overall region of convergence is the intersection between these two regions. So -1. So that's for the red line. It is for the first function, this one here. And the blue line is for the negative function. So the region of convergence is from -1 to 2. Is this clear? Do I have to do it? Okay. Okay. Another important, let's say, information we can get from the Laplace transform is the poles and zeros of this transfer function or the transform. You've done poles and zeros in mathematics too. So why they are important? The poles mainly. Because what are the poles? They are the zeros of the denominator. Assume that I have a rational function, something like 1 over s plus 3. So what is the pole in this case? S equal -3. Basically, it is the 0 for this one. So in this case, if s equal -3, what will be the value here? Infinity, because I'm dividing over 0. So in this case, the system will not be stable. So poles are highly associated with stability. That's for the Z transform. So here for the poles, if you look at the S-plane, all my poles, by the way, zeros are symbolized with a circle, poles with the X. All my poles should be negative to the, should be to the left of the S-plane. So this is S. So the pole should be there. So in this case, actually the function is stable. E to the power actually minus 3t, not u of t. So this is the transformation for this one. The location of the poles. You look at the location of the pole. If they are left to the S-plane, then the system is stable. Definitely, like, for example, I'm going to give you something like this. X of s equal 1 over s squared plus 3s plus 2. And I ask you, is this system stable or not? So just factorize it, 1 over s plus 2, s plus 1. So confirm s squared, s, 2s, that's 3s, 2 by 2, 2 by 1, that's 1. So I have a pole at s equal -2 and s equal -1. If you go to the S-plane, so that's the -1 and that's the -2. So in this case, the system is stable. Why? Because my poles are located to the left of the S-plane. If I have, for example, 1 over, for some reason, 1 s plus 3, s minus 1. So I have a pole at s equal -3, at s equal +1. So at the S-plane, so that is -3, and that is 1. So I have a pole at the right side. So in this case, the system is not stable. On the left side of the S-plane, or should be a negative value. But why not saying negative value? Because sometimes the poles are complex values. So complex values could be something here and here. So as long as they are at the negative side of the S-plane, then the system is stable. Clear? Right, so we'll go back to the slides. So the pole of a Laplace transform is the value of the s at which the transform tends to infinity, the 0 of where the function tends to become a 0. Okay. Pole zero to infinity. Poles and zeros can be illustrated in the pole zero diagram. Or basically you have to plot it. Again, poles are represented by x's and the zeros are represented by, I'll not call it O's, but yeah, it is O's, like X's and O's. But yeah, this is the X, that's the pole. And poles and zeros, they are always, if they are complex, they are always conjugates. Conjugates mean that they have the same imaginary part, but it is reversed in sign. All right, so we have this example. Find the Laplace transform of x of t, delta of t minus 4 over 3 e to the power minus t u of t plus 1 over 3 e to the power ut 2t u of t. Again, from the tables, so this one immediately it is 1. So this one's going to be 4 over 3, 1 over s plus 1, and 1 over s minus 2, 1 over 3. So that's for the first one. That's the second one. That's the third one. Immediately from the tables. You don't have to think. Okay. All right. Now to find the poles and zeros for this system, you have to unify the denominator, add them all, and you'll get this expression. So here you have a pole at 2, a pole at -1. And in this case, since we have a pole at 2, then the system is not stable. And you can actually check from this one. You don't have to use the Laplace transform. So this one, as t grows, this function will grow higher value. So it will tend to go to infinity. Okay, finding the inverse, as I mentioned, is not that easy. It's quite tedious. So we always refer to the tables. We simplify usually if we are given a rational or a fraction for the Laplace transform. What we do usually is to apply partial fraction expansion to convert it into some scalar value over s plus like a certain constant. And then from the tables, you apply the inverse Laplace transform. So for example, here you have, I think we've done the same for the Fourier partial fraction expansion. So here you have 1 over s plus 1 times s plus 2. So it will become a over s plus 1 plus b over s plus 2. And your task is to find the values of a and b. So once you find them, this one immediately is a e to the power minus t u of t and plus b e to the power minus 2t u of t. Right? Plus, no, hard to find if you want to apply the integration. But doing it this like this and apply the partial fraction expansion, it will be easier to do with the tables. But calculating this integral is not that easy. All right. So some analysis on the Laplace domain. Something we already know when we did the Fourier transform, the block diagrams. So when you have them in series, so that's a typical block diagram. When you have them in series, you multiply them, you have them in parallel, you just add them, and so on. So pretty straightforward, pretty much like what we did in Fourier. All right. Now, regarding system properties, we'll focus only on causality and Bibo stability. Bibo stability is bounded input, bounded output. And we've seen in stability, we check for the poles. If they are on the left side of the S plane, then the system is stable. Now, for causality, let's see the condition here. If this LTI system is causal, the impulse response should be causal, and therefore it is right-sided. From this, we have this result. By right-sided, the region of convergence, so assume this is the S-plane, and I assume that I have some certain constant alpha, and that's what we mean by causality. You look at the region of convergence, it's right-sided, so it is something like this. It's not left-sided, it's not bounded, and so on. We'll see some examples. So the region of convergence associated with the system function of causal LTI system is right half plane or the entire complex plane. What they mean by the entire complex plane is like this. So I'm taking all values of the complex plane. So something like this. So in general, the converse of the above theorem is not necessarily true. That is, if the region of convergence of the system function is right-hand plane for the entire complex plane, it is not said to be system is causal. Now, for rational systems, if the system is given rational, we have to like that the converse does not hold as indicated by the theorem below. So this is the theorem here. For an LTI system with a rational system function rational, something like this. Causality of the system is equivalent to the region of convergence of H being right half plane to the right of the rightmost pole, or if H have no poles, then the entire complex plane. So we'll see an example in this. For example, you have e to the power minus t u of t. We know it is causal, well, because we have the unit step function. Now, in this case, the region of convergence where S is larger than A, negative A, sorry, and A equals to 1. So here I have S, sorry, larger than, not less than, larger than negative 1. So here's negative 1. That's my region of convergence. It covers the entire imaginary axis. And it is right half plane. So in this case, it is causal. So the Laplace transform is rational. So we are applying basically this theorem here, but without going into the details, it just simply it is right half plane, so it is causal. The right hand, the system is causal. Another example here, e to the power minus absolute value of t. And we notice here that there is no step function. So e of t will have like with this, I almost say weird looking, but it will have all values of t, so 0, something like this. So in this case, we have points in negative in time. So in this case, the system will not be causal. Okay, so here, since h of t does not equal 0 for all negative points in time, then the system is not causal. Also from example 9.7, I think that's from the book, the transformation, the Laplace transform for this function, it's this result. In fact, you can simply do it like this, h of t equals e to the power minus t, that's for t larger than 0, and e to the power t for t less than 0. Because minus absolute value of t. So what is the absolute value of t? Equals t when t is larger than 0 and negative t when t less than 0. So substitute this in the exponent. So we are having this. So we're having two functions. Find the integration for each one of them, or find the Laplace transform for each one of them, and check their region of convergence, and realize that the system will not be causal. So that's the region of convergence here. And there you go. So you have this expression. Now, when you look at the region of convergence, it's not the entire right half plane. It's bounded between -1 and 1. So in this case, the system will not be causal. Clear? You get the idea here?
Does it going on the whole right side?
The whole right plane. Like in this one here, I stopped at 1, and this is -1. So this is my region of convergence. This one is not covered, so in this case, it's not causal. So here, thus, h of s is rational and has a region of convergence that's not to the right of the rightmost pole. All right. Okay, Beam stability, well, as I mentioned, we look at the poles. They should be at the left side of the S plane. So for example, here, the system has a pole at 2. So here, in this case, is not stable. And we can tell that e to the power u of t, e to the power 2t times u of t, it's something like this. It will keep growing as time grows. It's exponential. Okay, so this function here, check if it's stable or not by looking at the poles. You don't even have to do the partial fraction expansion. So here I have a pole at -1 and another pole at 2, so it's not stable. Now regarding region of convergence, and here to check if it's causal or not. So here it is at the right side plane, so it is causal in this case.
It's not
You mean the entire imaginary axis? No, it should be at the right of the rightmost pole. So here, let's say we're not sure about ROC, so assume causal system. So region of convergence must be to the right. You know what? Let's do the analysis. Let's not jump into conclusion. We need to find the inverse Laplace transform for this. So let me take it. And we can tell actually from the time domain once we find the inverse here, whether the system is causal or not. Linear time invariant system. We should not forget this because we spent a lot of time at the first half of the course. LTI, linear time invariant. We did linearity test, time invariance, if you remember. So linear and time invariance. And for linearity, we have the additive feature and superposition, scaling, and so on. Okay, so I have the function here. It depends on the question if it's required. Like if I ask you, check if the system is stable or not, find the poles and immediately you can say it's stable. Now, if I ask you, check if it's causal or not. Like this. Now, let's assume I gave you this question and check if the system is causal or not. So let's do the inverse Laplace transform and check. So here I'm going to get A over S plus 1 plus B over S minus 2. Okay, cross multiplication. So I will have A S minus 2 plus B S plus 1, and that should equal to S minus 1, right? Again, if I want to put the denominator, S minus 2, then compare side by side between this and this, I will realize since the denominators are the same, the numerator has to be the same. All right, so let's try at S equal 2. So in this case, A 2 minus 2 plus B 2 plus 1 equal 2 minus 1. So in this case, B equal 1 over 3, right? Let's try the other case at S equals negative 1. So here, A negative 1 minus 2 plus B negative 1 plus 1 equal negative 1 minus 1. So in this case, this will be gone. I have negative 3 here. I have negative 2 here. A equal 2 over 3. So in this case, I will have the following. A over S plus 1. So let me put the value of A exactly. So A is 2 over 3 over S plus 1 plus B 1 over 3 over S minus 2. So this one leads to what? 2 over 3 e to the power minus t u of t plus 1 over 3 e to the power 2t u of t. Now again, since we put the u of t, immediately that's a causal system because u of t will force the negative values in time to be 0. Clear? Again from the tables. Now, why is saying here assume a causal system? What does that mean? Like, could the system be not causal? Remember, Laplace pairs are not unique. Like, I could have two exact systems with the same Laplace transform. The difference will be the region of convergence. Now, this one, if I have, for example, this one, let's take this one as a special case. This one, another representation could be negative e to the power minus t u of negative t. If you go back to the tables, we don't have to worry about how I got the expression, but here. So e to the power negative at u of t, it's 1 over s plus a. Now the other, see, like notice here, they are the same. Okay, let me do the eraser. Now notice these are the same. So I could get this one, or I could get the other one. So the first one is e to the power minus 80 u of t. That's causal system because I have u of t. Then the other one, I have negative, same exponent u of negative t. This is not causal because I have negative time. So both of them are correct inverse Laplace transform for this. But that's why I said assume causality. In the question, it says assume that both systems are okay here. Rational, the question after, yeah. Assume causal system. So you've seen why we came up with this assumption that it's causal. So you could have a causal and not causal of the same Laplace transform. But we always assume causality. No, in the question, I will not say check if it's causal or not, because it depends on how you're going to do the inverse transform from the tables. You can pick the first one or pick the second one. So in that case, yeah, in the exam, I will not ask check if the system is causal or not, because it could go both ways. Okay? Yeah, you will assume it is causal. Just check for stability. Focus on the stability part. All right. Invertibility is something easy. Invertible transfer function, that if you have a system with a certain transfer function, find the other system with that when they are in cascade or they are in series, the output will be 1, will lead to 1. So that's the inverse. So it is something like this. Basically, assume that there's a system H of S, and there is another system here, H inverse of S. And if I apply x of t, x of s, I should get x of s. Why? Because their equivalent is 1. H of s, and I have h inverse of s, their equivalent is 1. So if my input is x of s, the output should be x of s. Clear? Okay. Differential equations, pretty much like what we did in the Fourier transform. You will be given a system of differential equation and solve, like find the impulse response, for example. And we'll finish it with this example here. So here are some expressions here. You will be provided with these expressions. And the little bit difference between Laplace and Fourier. In Laplace, we have to worry about the initial value condition. If it's not given, you assume a 0 initial value condition, but if it's not, you have to put the value there. So the Laplace transform of the first derivative here, it's S times the Laplace transform of f minus f0, which is the initial condition of the function at 0. If it's the second derivative, it's s squared f of t minus s f of 0 minus f prime of 0, and so on. And I think will not need this, or mostly will be focused on the second derivative. So during the exam, expect something like the second derivative. And you'll be given the values of the initial value conditions. So for example here, y prime of t will lead to s y of s. And if you see this value or this expression assume 0 initial condition, means that y of 0 is 0, y prime of 0 is 0, and so on. Y double prime of t will lead to s square, y triple prime, that's the third derivative, s cube y of s. All right, so let's see this example and we'll finish the lecture. Okay, Control C. Okay. So let's consider this linear time invariant system, which the input x of t and the output y of t, they have this relationship between the input and the output. Now, the question is determine if the system is stable or not, and find h of t from h of s. Now, notice here I did not mention any information about h of t and h of s. But what do we know? What's the relationship between h of s, y of s, x of s? h of s equal y of s over x of s. So in here we can get y of s and x of s and evaluate this expression to get the transfer function of the system. All right. So let's see here. If it doesn't mention any initial values, then assume zero initial value condition, assuming zero initial value condition. So in this case, we'll go back to the question. Let's apply Laplace transform. So we'll get s y of s plus 3 y of s. So that's the transformation here. That's Laplace. Here, Laplace equals x of s. So I applied Laplace transform for each element of them. Here we can easily take y of s as a common factor. It's going to be s plus 3 equal x of s. So to evaluate y of s over x of s, I'm going to get 1 over s plus 3. And that's h of s. Is it stable or not? Find the poles. Pole at -3. So that's the s plane, -3, left side of the s plane, so it is stable. So check if the system is stable. It is stable. Now find h of t from h of s. So we find h of s. H of t from the table, we have e to the power minus at u of t. Laplace pair is 1 over s plus a. So in this case, h of t equals e to the power minus 3t u of t. And that's it. So that's for a first order differential equation. Second order is no difference.
When you picked.
No, you always assume causal system for practical reasons. So you always look for the causal one. If you pick the anti-causal one or the non-causal one, it is not wrong. If it's not mentioned here, that assume that like if it's a causal system or not. So you have the freedom to pick whatever you want. So you have the choice to either pick this one or -8 or -3t u of -t. Up to you. But you always, look for a causal system. Is it clear? So this is going to be the topic, inshallah, for next week in the quiz. We'll talk about Fourier and this Laplace transform. Assume questions will be related to the differential equations, Fourier coefficients, etc. Inshallah, remind me, send me an email about the details of the quiz. And I'll try to be as detailed as possible.
There.
Quiz sample, we don't do quiz samples. But once I give you the, let's say, like the samples, just look at the slides. Because if I tell you, okay, we'll solve differential equations, solve the examples. That's because the quiz sample will be no difference from the, let's say, from the scope of the slides. I'm not gonna give you like some question from Mars. It's gonna be something from the same level of the slides. All right. Okay, so stop sharing. Stop recording.